This is the video demonstration for path planning for simple robots using soft subdivision search. We've implemented our algorithms for a disk robot with 2 degrees of freedom, a triangle robot with 3 degrees of freedom, and a 2-link robot with 4 degrees of freedom. In this video, we present resolution-exact algorithms for path planning. Here's an example of a path found for a disk robot in an environment with 3 polygonal obstacles. The subdivision algorithm begins by finding a free box containing the start configuration. Similarly, it finds a free box containing the goal configuration. Finally, boxes are subdivided until there is a free path from beginning to end. Here we give the basis for the correctness of our algorithms based on resolution exactness. First, the algorithm has a constant k greater than 1 independent of the input. There are 2 conditions for the resolution exact algorithm: path and no path. In fact, for a given epsilon, if the greatest clearance is between epsilon over k and k times epsilon, the program may print either path or no path. This is an area of leeway for the program. In this clip, we illustrate these 2 conditions. For this environment, the program's output was no path, as seen in the lower right panel. If we decrease the radius of the robot from 8 to 7, then the program outputs path found and displays the path. Notice that if we keep the radius at 8 and decrease epsilon from 2 to 1, the program again outputs path found, since it is now searched with finer resolution. Our algorithm depends on a classification of boxes. Resolution exactness opens the way for a soft classification, which intuitively means that they can be implemented by numerical approximation. The classification has 3 possible outcomes: free, stuck, and mixed. Free and stuck are definitive answers, and the soft predicate is set to be conservative if it never makes a mistake when it outputs a definitive answer. The other requirement of softness is that it converges in the limit to the correct answer. This display demonstrates the classification of the boxes and their color code. Notice that boxes smaller than epsilon are colored gray. Here we show the color coding for the triangle robot. The color of a square in the display represents the projection of the colors of the x, y, theta boxes onto the xy plane. In the projection, the colors are blended, so if a yellow and a green box are projected onto the same square, it will be displayed light green. The algorithm is controlled by a priority queue, which contains boxes that are mixed and greater than epsilon in width. The algorithm terminates when a path is found, or if the queue becomes empty. Here is a demonstration of the priority queue. A box of highest priority is taken from the queue. The priority of a box depends on the search strategy. The box is split into 4 children, and the children are then classified. Any children classified as mixed are then reinserted into the queue. The getNext method of the queue represents the global search strategy. We use several search strategies for the priority of the queue. Note that the choice of strategy does not affect correctness, but may affect performance. Here is a demonstration of the triangle robot amidst an environment of 200 randomly generated triangles. Using the breadth-first search strategy, a path is found in 265 seconds. Here is a visualization of the classification of the subdivision boxes. Here is another demonstration using the greedy best first strategy. This time, a path is found in 15 seconds. Here are the box classifications for the greedy method. Here is a demonstration using the random strategy, which consistently takes longer than the others. In this instance, it took 353 seconds. Here are the box classifications for the random method. Finally, here is a demonstration of the Voronoi heuristic. In this instance, it took 30 seconds to find a path. Much better than the random strategy, but not quite as good as the greedy best first strategy. We now look at the two-link robot. The two-link robot has 4 degrees of freedom, 2 spatial and 2 angular. The configuration space of the angular components is topologically a torus. The boxes visualized here are really the projection of the 4-dimensional boxes to their xy coordinates. This environment consists of 8 corridors converging on a central atrium, with 3 small obstacles within the atrium. Here is the same environment with the Voronoi heuristic selected. In this case, a path was found in 1.2 seconds. The random strategy took 2.5 seconds. The breadth first search strategy took 3.1 seconds. And finally, the greedy best first strategy took only 0.7 seconds. We also implemented a version of the two-link robot where self-crossing of the two links is forbidden. Here, θ1 may not equal θ2. In the torus picture, the forbidden configuration corresponds to a diagonal line. Notice that the configuration space is still connected. We can generalize this forbidden diagonal to a forbidden band around the diagonal to forbid the links from coming within a certain angle of each other. Here is a solution to the inverted T-room environment where crossing of the links is allowed. Notice that the path is quite simple. The robot simply moves up as it crosses its links. And here is a solution where the two links may not come within 5 degrees of each other. Notice this time that the robot is forced to take advantage of the bar at the bottom of the T. Finally, if we increase the bandwidth from 5 degrees to 6, no path is found.